Hello everyone. Today we'll be solving problem number 124, binary tree maximum path sum, right? So what the question states here, we are given a binary tree. Just give me a second here, 1 second. Yeah, we are given a binary tree. We have to find the maximum sum of any non-empty path. So we have to find maximum sum of any non-empty path. A path is a sequence of connected nodes. A path is a sequence of connected nodes. No cycles can start and end anywhere. No cycles can start and end anywhere. So each node value can be positive or negative. Each node value can be positive or negative. We have to return the maximum path sum over all possible paths. Again, I'm telling, we have to return the maximum path sum over all the possible paths, right? So what are the conditions that they have given? A path is nothing but a sequence of connected nodes. They have strictly mentioned no cycles and it can start and end anywhere. And also we have been given each node value that can be either positive or negative. All we have to do is we have to return the maximum path sum over all the possible paths, all the possible paths, right? So here in this case we are considering 213, 213. So the optimal path here is 213 with a path sum of 213 when we have considered nothing but here 2 plus 1 plus 3, man, 3 plus 3 nothing but 6, right? So the optimal path is 6. The output that we need to return here is 6, right? So just give me a second here. Yeah, let me come to the second example here. So here the optimal path we need to consider, just give me a second, 1 second. So yeah, we have minus something, just give me a second here. Yeah, here optimal path is 1527, 1527. Because if we consider minus 10, it goes negative, man, it goes negative, right? So if we consider this one means this is not the optimal path, sorry, it doesn't go negative, sorry, I'm extremely sorry. This one, it doesn't go negative, basically the value doesn't go negative, but the optimal path sum will be smaller. We have to go for the optimal path sum, right? Optimal path sum. So the sum will be getting here would be smaller if we consider this one, this part, right? This part and basically this part, right? So we'll ignore this one and we'll be going with a 1527, this path. So this path I have considered, right? So this will be 15 plus 20 plus 7, 15 plus 20 plus 7. This will lead to 35 plus 7, nothing but 42, right? Nothing but 42 here, right? So we need to return 42 as output. So I hope the question part is completely clear, man. I hope the question part is completely clear. They have given us wonderful examples just for the sake of understanding, right? So here I hope the question part is completely clear. Let's discuss the this one. Let's discuss approach followed by the complexities and then let's write the code. Initially, let's discuss the approach first. So let's consider first example, this itself, 1 2 3. So we have here 1 2 and 3, right? So first what we will do, the first thing that I want to tell you here is we will be going with a post order DFS traversal, right? Post order DFS traversal, right? So when I say post order DFS traversal, uh, I'm speaking of this one. What do we call? Mm, so when I say post order DFS traversal, so we will be performing the DFS, right? So we'll be making use of the this one, helper function DFS. This is fine. Uh, yeah, we'll be going with the recursion as well, right? So this will be recursive DFS basically. This will be recursive DFS, and also we'll be going with a post order traversal. Post order follows the order left followed by right followed by root followed by root. Always remember this one. So we have already solved n number of problems on post order, pre-order and in order traversal, right? So here again, previous problem also we have solved on post order itself, post order traversal itself. So post order traversal follows the order left, right, and then root. So the approach that we'll be going with here is post order traversal, along with the post order DFS traversal, you can call it, right? So we'll be going with a recursive DFS as well, right? So just keep this in mind. So the first part here would be, so a valid path can be just one node. either it can be 2 or it can be 3. The first example we have considered, right? So or we are considering here. So a valid path can be just one node, 2 or 3, or go across nodes, nothing but 2 1 3, right? 2 1 3 again, right? So a valid path can be just one node, either it can be 2 or it can be 3, or it can go from 2 1 3, 2 1 3, right? So at node 2 maximum path down is 2, maximum path down is 2. This one we are considering the node 2, right? So at node 2 the maximum path down is 2. At 3 it is 3, at 3 it is 3, we don't have the subchildren. At 3 it is 3, at 2 it is 2 only, right? So at 1 the best path including both the sides is, if we are considering 1, then it is 1 plus 2 plus 3, 1 plus 2 plus 3, or we can consider 1 1 plus 3 plus 2, or we can consider 1 plus 3 plus 2, right? So both will yield us to the output 6, both will yield us to the output 6 here, right? So at 1 the best path including both the sides is 2 plus 1 plus 3. So as a whole we are considering here, right? Maximum optimal path sum we need to find. So we are considering as a whole, this will be 2 plus 1 plus 3, nothing but 6, right? So next what we will do, we have to keep track of the maximum path including both sides, right? Including both sides. This can be answer, or we have to go with the maximum one side path to pass up to the parent, nothing but this one, 1 plus maximum of 2 comma 3, 1 plus maximum of 2 comma 3. For the second example we are ignoring the minus 10, we are ignoring the minus 10. In this case we don't have to go with this one, we can just go with directly 6. Till here it was completely fine, right? Till here. So for we have to consider all the edge cases or all the test cases, right? So here in this case we have to consider, first thing is maximum path including both sides, that can be answer as well, or we have to consider maximum one side path to pass up to the parent, nothing but here in this case we have to go with 1 plus max of 1 plus max of 2 comma 3, 1 plus max of 2 comma 3, right? So this one, this can be answer as well, right? So I'll just delete this one. The approach that we went with here is post order DFS traversal. Post order DFS traversal. At each node, we need to compute left and right max path sums. At each node, we have to compute left and right max path sums only if it is positive. And we have to update the global max sum with left plus root plus right. Means we have to go with the path through the current, right? Through the current value, and we have to return to the parent, nothing but root plus max of left comma right for the further recursion. As I have said, we'll be going with the recursion, right, or the recursive DFS. So we have to return to the parent, nothing but root plus max of left comma right for further recursion. So this is the approach that we'll be going with. This is the approach that we will be going with. In this case, we have got the output 6, which is equivalent to the output that they have mentioned for the example 1. Example 1 within the question. So our approach works absolutely correct. As we are completely familiar with the approach, let's continue with the complexities part. So what will be the time complexity here? The time complexity would be big of n. The time complexity would be big of n, because we are visiting the each node exactly once in the post order traversal, post order or post order traversal, right? So overall time complexity would lead to big of n. And what would be the space complexity here? The space complexity is big of n as well. The space complexity is big of n as well, because we are going with a recursive stack. The recursive stack can take up to big of n depth. The recursive stack for the DFS can take up to big of n depth, but in our case, if the tree is balanced, it can take up to big of logarithmic of something, big of logarithmic of something, right? So it is better to take the height of the tree rather than going with the balanced tree or for the skewed tree, balanced tree or for the skewed tree, right? So overall, let's consider h here. Overall space complexity would lead to big of h, big of h, because we'll be considering the recursive stack depth, where h is nothing but the height of the tree here. So overall space complexity would be big of h in this case. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of 1, a big of n and big of h respectively. So now, as we are completely familiar with the approach and the complexities part, we are good to write the code. Let's start writing the code. So first thing what I'll do here is let's store the global maximum path sum. First, let's store the global maximum path sum. So I'll just come here. So this is the global variable, right? So I'll just go with mm, private. So this one is max sum. Let's assign this one to integer dot min underscore value. So we are just storing the global maximum path sum here. So within this method, max path sum method, so we have the parameter root here, right? So we have to perform DFS. Let's do one thing. Let's make use of the helper method DFS here. Let's perform the DFS and then let's make use of the helper method DFS within the main function, right? I'll just come out of this one. I'll just go with private int DFS of tree node. This will be node. This is fine. So within this method, so let's go with the base case now. Null node, right? So null node, if the node is null, then we have to return 0, right? So I can just write in this way: if node equals null, then we will return 0. So the next part here would be we have to recursively get maximum gain from the left and right subtrees. Means here I'll just go with int left equals math.max of 0 comma dfs of node dot left. So this is fine. We are just ignoring the negative paths here. So here it will be int right equals math.max of 0 comma dfs of node dot right. So this is fine. So the final step here would be we have to compute the local max path. Means we have to include both sides of the current node here, right? So this will be local max. This is equal to, we have to go with here this one left plus right plus this one node dot val. This is fine. So let me do one thing. Now let's update the global maximum if the local is greater, right? So I can just give here maximum and let me assign this one to math.max. We have to go with the maximum, right? So this will be maximum itself. So let me copy this one and paste it over here variable, and also we will be going with the local max. Basically from the local max itself we are getting the maximum value, right? So this is fine. Then final step here would be we have to return the maximum one side path that is to be used by the parent, right? So we have to return maximum one side path that is to be used by the parent. So I can just write here return node.val plus math plus why did I give this one here flower bracket? So this one will be math dot max of this one left comma right. So this is fine. This is fine. Yeah. Let's make use of the DFS method. Let's make use of the helper method DFS within the main function now. So I have left here, right? So we have performed DFS successfully. Post order DFS traversal or recursive DFS. So I'll just go with here DFS of root. We have to start the DFS from the root, right? So we are starting DFS from the root and we have to display the final result that we have stored in the that we are storing in the maximum sum. So here I'll just go with return max sum. So this is fine. So we are done with the code. Let me format the code once and let me hit the run button. I hope this works, man. Let's see. So yeah, here a I have to make this one small a. We run this one again. Again the same mistake, man. We run this one again. So let's wait for some time, man. Yeah. Yeah, you can clearly see here the sample test cases are getting passed. Means let me hit the submit button here. I hope this works for all the test cases, man. Let's see. Here you can clearly see all the test cases are getting passed, means the code works absolutely correct on this case. The code works absolutely correct on this case, right? So I hope whatever the code that we have, I hope the coding part is completely clear. I hope the solution part is completely clear along with the complexities as well as the approach. For now, this is it. Thanks for watching, guys.